So this week is going to be about NP and NP completeness, the lectures you've been waiting for, right? So we're going to have two lectures on this. This lecture will focus more on the big picture, and next lecture we're going to go into more detail about these things. Okay, so let's start. So you guys are computer scientists, most of you, or programmers, and you all should have certain tools in your toolbox. Okay, so first thing you should know about is basic algorithmic techniques. Okay, so you're probably going to learn more about these kinds of stuff in future courses. We've seen some already in this course, but basic algorithmic techniques includes things like greedy algorithms, divide and conquer. So for example, merge sort is divide and conquer, or the Karatsuba multiplication algorithm is divide and conquer. There's dynamic programming, there's linear programming, there's semi-definite programming, and so on. So these are like general purpose algorithms that allow you to solve a wide range of computational problems. Okay, and very useful techniques. You should also know about your basic data structures. Okay, so these are ways to store and maintain data in your programs. So you should know about, for example, I don't know, queues, stacks, hash tables, binary search trees, and etc. And depending on what you're trying to do, one data structure can be much better to use than another data structure. You should know which one to use when. We're kind of censored, but you can check this side, I guess. The third thing you should learn about is identifying and dealing with intractable problems, because the world is not very nice. You're not going to always come across problems that are solvable efficiently. Sometimes, I mean, not sometimes, I can guarantee you that at some point in your life, you're going to come across in some project you're doing, some problem that's basically going to be hard, computationally hard. Maybe your boss is going to give you some problem and say, can you please solve this problem? And maybe that problem is going to be hard. Now, you have to be able to identify if a problem is hard. You don't want to work months, years trying to come up with an efficient solution if there's good reason to believe that there actually does not exist an efficient solution. Okay, so this is definitely an important thing you have to know how to do. And this lecture is basically going to be about this third step, trying to identify problems that are intractable. How to deal with them is, I guess, a separate question, and we're going to look at that next week, actually, on Tuesday when we talk about approximation algorithms. And that's one way of dealing with them. But first, we have to identify these problems. Okay? So let me give you some examples. Some examples that you might come across, that your boss might give you, and ask you to come up with an efficient algorithm for. So, and all of these problems that I'm going to present are quite central problems that every computer scientist should know and does know. Okay, so the first one is like knapsack problem. So here we're given n items. Each item has some value and also some weight associated with it. The parentheses doesn't really matter. Yeah, they have to be non-negative integral. Don't think about that for now. You're also given some capacity, capital W, and a target value T. Okay, and basically the goal is to figure out, is there some subset of the items such that the value of these items are at least T, sum to at least T, subject to the constraint that the weights should sum to at most W. Okay, so this is, the way you can think about this is like, let's say there's some robber trying to rob your house. Okay, he has a knapsack, but it's, he can only carry, let's say, 15 kilograms. He looks around the room, he sees items, they have different weights, and they also have different values, right? And he's trying to basically maximize the value he can get from the items, but of course he's limited to just 15 kilograms. He can only carry that much. So which items should he then put in his knapsack? So that's sort of the way you can explain this problem, but it's really a very general problem. It comes up a lot in different settings. The capacity is like, you can think of it as a budget you have. The rates are like the price you have to pay to get that item. The value is how much you value that item, and so on. So you can think of it that way as well. And in this lecture, we're always going to be talking about decision problems. Those are problems that have a Boolean output, yes or no output. You can also talk about the optimization version of this problem. You can say, what is the best subset? Find me the best subset, output the best subset. But, restricting ourselves to decision problems is sort of basically without loss of generality, and it's easier to deal with, so we're just going to focus on decision problems. Here's another very famous problem, the traveling salesman problem, or TSP in short. Here you're given some graph, G, and each edge on the graph has some weight, W sub E, non-negative integral, and some target T, target integer T. And the goal is basically to output yes if there is a cycle in this graph of cost at most T that visits every vertex exactly once. Okay? So, for example, maybe this is your graph. You have your edge weights. And usually, actually, this graph will be given to you as a complete graph. Every edge will be present in the graph. And basically, if you don't want an edge to be present in your graph, what you can do is you can assign like an infinity, weight infinity to that edge. That means like you really shouldn't be using that edge because it's going to affect the cost a lot. But anyway, so let's say this is some graph it's given. You want to find some cycle. In the optimization version, you would want to basically find the minimum cost cycle that visits every vertex. And I think if I didn't make a mistake, this is minimum cost cycle in this graph. And this is, again, a very general problem. It can come up in various settings. So for example, you can say, here are the cities that I want to visit in the world, a bunch of cities. Going from one city to another city costs something if I buy, let's say, a plane ticket. And I can ask, in which order should I visit these cities so that, let's say, I minimize my cost? Or if I want to make a decision problem out of it, I can say, in which order should I visit so that, let's say, the cost is at most $20,000 or whatever. Okay. Another very important problem that we've seen before, satisfiability problem, SAT. So you're given a Boolean propositional formula, something like this, and you want to know if there's an assignment to the variables that makes this formula true. Okay. Another problem, theorem proving problem. This is the problem that Kurt Gödel wrote to John von Neumann about. So he said, like, given a first order logic formula and some target length T, we want to know if there's a proof of that formula in the FOL, first order logic deductive calculus, of length at most. So a very fundamental problem. If we could do this efficiently, it would have very interesting consequences. And Gödel actually, if you remember in his letter, was optimistic that maybe there is an efficient algorithm for this. Okay, but here's the fact, okay? So these problems have come up in various different settings. And people have been trying for decades to solve these problems efficiently, to find an efficient solution, and no one has been able to succeed in this. Okay, so we have not been able to come up with efficient algorithms. Now, and to be honest, most people don't expect that there is an efficient algorithm for these problems. And it would be great if we could just prove that. And we just say, you know what, here's a proof that the SAT problem cannot be done in polynomial time. But polynomial time is a big beast, okay? It's a very powerful class of, there's a very powerful class of algorithms, okay? They can do a lot of tricky things. We sort of saw some of them in this course. And we have this big beast. We are trying to show that it cannot do SAT, it cannot do TSP. And you know, we've tried everything, we've thrown everything at it, and we cannot even scratch the surface of this beast. Okay, we don't even come close to it. So we are clueless about this, directly proving that it cannot be done in polynomial time. Okay, then you know, should we give up then, right? So what can we do? Well, if we cannot directly prove it, and I mean the other thing you should ask yourself is maybe these problems are in P, right? Who knows? It could possibly be in P too. But okay, so you don't believe, let's say, they're in P. What can you do if you cannot prove that they're in P? The next thing you can do is basically try to gather as much evidence you can find to support this claim that these problems are actually hard. Okay, and this is basically going to be our goal in this lecture. We're going to try to somehow gather evidence that these problems are indeed hard, and that's the best that we will be able to do. And yeah, and I mean, it's quite surprising maybe, but we will be able to do this, okay? And these things, this goal is going to lead us to the notions of NP hardness and NP completeness. And these terms, NP hard, NP complete, they are basically synonyms for computationally intractable. And you all have to know what these things mean. So I realize that everyone in this room have different interests. You may not be interested in theory, for example. You may, you know, graduate from CMU and forget about what the definition of a Turing machine is. You may forget what the definition of a deterministic finite automata is. And you may never see those things again in your life. That's a possibility for sure. But when it comes to NP hardness and NP completeness, you have to know these things, always. If you want to call yourself a computer scientist, a programmer, or whatever, you have to always know these things and definitions. And in fact, not only you, but everyone, every scientist, every engineer should know these terms, what they mean. Okay, because as we discussed in the first lecture, computation is basically everywhere. In every field, people are trying to solve computational problems. And in every field, these intractable problems are going to come up, for sure. Okay, so when they do come up, when you do see these problems, how can you identify them as intractable? And how do you deal with them? You have to know these things, okay, if you're a scientist or an engineer. All right, so our goal is to find evidence, say, let's say TSP or SAT, whatever, pick your favorite problem, is computationally hard. Okay? So let's see how we can do that. And to do that, we're going to revisit a notion that we've already seen before, and that's reductions. Okay, so this concept is a very useful concept in computer science. And it's a way, as we saw before, is a way to compare the difficulty of problems. Now, what we mean by difficulty will depend on the context. When we saw it for the first time, the context was that we're interested in problems that are either decidable or undecidable. So undecidable problems were difficult, and decidable problems were okay. But now we're going to refine that, okay? So in this context right now, we're interested in polynomial time decidability versus, well, not polynomial time decidability. Okay, and our goal, again, is going to be basically to define this notion. So if we have two computational problems, two decision problems, or two languages, A and B, we want to define this notion A less than or equal to B. Okay, and what this is supposed to mean is that B is at least as hard as A, right? B is at least as hard as A, with respect to, of course, polynomial time decidability. So to be more precise, what we want is that when we write A less than or equal to B, then it should mean that if B has a polynomial time algorithm, then that should imply that also A has a polynomial time algorithm for it. Okay, if B is in P, then A is in P. If you take the contrapositive of this statement, it means it's equivalent totally to this. If A does not have a polynomial time algorithm, then B does not have a polynomial time algorithm. Right? If A is not in P, then B is not in P either. Okay? So we want to define this notion, and we can do it simply as follows. So last time we saw reductions, we had A less than or equal to B with a subscript T. T was for a Turing reduction. Now we're going to also add a P to that notation, P for polynomial time. So we're going to say A polynomial time reduces to B if it is possible to decide A in polynomial time using an algorithm that decides B in polynomial time. Or in other words, if you were to give me some polynomial time algorithm for B, this box that solves B correctly in polynomial time, then I could come up with an algorithm that solves A in polynomial time, and it's going to make use of this subroutine, this algorithm, when it's doing so. And it can call this multiple times if it wants to, right? It's not restricted to call this algorithm just once. You can call it multiple times too. Okay? So why do we say A reduces to B? We say A reduces to B because basically what we're saying here is that the problem of finding an efficient solution for problem A reduces to the problem of finding an efficient solution to the problem B. Okay? So all we need in order to describe an efficient algorithm for A is an efficient algorithm for B. That's the missing piece. If we can do that, we can do this. Yeah?
Then the Turing reductions are get us into trouble sometimes, because suppose that we take B and then we invert the answer, but then P and co-NP aren't the same thing.
I haven't defined NP co-NP yet, right? So we can discuss this later, though. Okay. But I mean, this is a totally valid definition. But I'm not concerned about co-NP right now. Okay, so so this is totally fine. So another way, if you want to look at it, is you're comfortable with code, you like Python, you can say, okay, suppose you have this function small b that solves the computational problem capital B, okay, some code, and suppose that you can come up with this function small a that basically solves the computational problem capital A, and it makes calls to this small b whenever it wants to. Okay? And then we say that, well, if the fact that if B is efficient implies that A is efficient, if my B function there is efficient, and that implies that then my A function is efficient, then we basically can write that A reduces to B, polynomial time reduces to B. And notice that, if you want to show that A reduces to B, what you want to come up with is this function, basically A, small a, right? Assuming this B exists somehow, it does what it's supposed to do, you have to come up with the A, show me the A, and then that will show me that, oh yes, indeed A reduces to B. Let me give you some examples, okay, 2 examples. So I'm going to give you 2 problems, A and B, and then we're going to see that basically A polynomial time reduces to B. The first one is going to be quite simple, straightforward reduction. So the first problem is, given a graph and an integer k, does there exist at least k pairs of vertices connected to each other? Okay. And the second problem is, given a graph and a pair of vertices, S and T, is S and T connected? Now I claim that A polynomial time reduces to B. Why is that? Exactly. So what I'm saying here is that if you could solve B efficiently, then you can solve A efficiently. Because if you can solve B efficiently for a given pair of vertices, you can check if it's connected or not efficiently. Well, then to solve A, I will just go through all pairs of vertices in the graph and run this algorithm for B and check, are they connected? And then just count the pairs of connected vertices, pairs of vertices in that way. And then if that crosses the threshold K, we're good. Okay, so an easy example, but this is a reduction. Okay, is a, again easy, but maybe slightly more complicated one. So the problem A is going to be now, given a sequence of integers and a number k, is there an increasing subsequence of length at least k? So maybe you're given the sequence like 3, 1, 5, 2, 3, 6, 4, 8. And you're trying to see, is there a subsequence of length at least k? Is there an increasing subsequence of length at least k? So these red numbers, they form an increasing subsequence, right? 1, 2, 3, 4, 8. And you want to know, if this is more than some threshold. Okay. The second problem, B, is as follows. Given now 2 sequences of integers and a number k, is there a common subsequence of length at least k? So maybe you're given these 2 sequences. The first one is exactly the same as the up there. And then maybe you're given some other sequence like this. And if you look at this, these 2 sequences share this common subsequence, which is 1, 2, 3, 4, 8. Now the claim is that A polytime reduces to B. How can you show that? Yeah. Randomize? Find the max? Generate one to the max.
Generate a sequence of 1 to the max. And then compare the 2 sequences.
So, okay, so we want to, I think you're on the right track, yeah. So we want to solve basically the problem A. We want to solve that problem. But good thing is we can assume that we can do this for free in polynomial time. Well, how would you solve problem A if you know how to solve this? Well, what you can do is, I'll just tell you, take that sequence at the top, so you're given this input to problem A, and then sort that sequence. Okay, so now you have 2 sequences. You have the original sequence, and you have the sorted version of that sequence. And now I'm going to run this algorithm on those 2 sequences. And I'm going to look for the largest common subsequence. Or I'm going to check, is there a common subsequence of length at least k? And that answer will correspond to what I want. Okay, if you think about it. It's not hard to see. Okay? So that's nice. So these are examples of reductions, and basically there are two sides to reductions. Okay, we kind of saw. The first side is the nice side. Okay, it expands the landscape of tractable problems, polynomial time solvable problems. Okay, why? Because as we said, if A is reducible to B and B is tractable, then A is tractable. If B is in P, then A is in P. And using reductions, basically, you can come up with new polytime algorithms for new problems. So like when you are given a problem to solve, a new problem, what you should do is first check, is this a problem that I already know how to solve? Okay, it might be a problem that you already know how to solve in disguise. So for example, your boss might come to you and say, you know, I have these jobs that need to be taken care of. There's these machines that can do those jobs. And I want to assign machines to jobs so that these things get done. And then you say, you know what, that is actually a matching problem in bipartite graphs in disguise. And I know how to do that. So you can do that. Now, sometimes that's not going to be the case. You know, it's not going to be exactly a problem that you know how to solve. But it can still be, often it's still going to be the case that it's similar to a problem that you know how to solve. So you should always think about, can I reduce this problem to a problem that I know already how to solve? Maybe I massage it a little bit, tweak it a little bit, and then it becomes a problem that I know how to solve. Okay, so that's one side of reductions. It expands the landscape of tractable problems. Now there's another side of reductions, the dark side. So you expand the landscape of intractable problems. Okay, so why? Because we also know that, you know, if you take the contrapositive, if A is less than or equal to B, if A reduces to B and A is intractable, then B is intractable. So if A is not in P, and then B is not in P, right? The problem is that we're pretty lousy, as I discussed, we're pretty lousy at coming up showing that a problem is intractable. So if we could show that there's some A that is not in P, and we could show then that A reduces to B, fine, then we know B is not in P either. But we cannot even show really for any meaningful language it's not in P. Okay? So even though this seems like a nice tool to expand the landscape of intractable problems, there's no starting point to do that, really. But that doesn't mean that this side of reductions is totally useless. Okay, and we're going to see now actually how we can make use of this side, even though we cannot prove that something is not in P. Okay, so going back to our goal, right? So we want to show, let's say, that SAT or TSP, we want to gather evidence that these problems are not in P. So you want to find evidence that, let's say, some problem A is not in P. Okay, so suppose we can do the following thing now. We can show that L reduces to A for many, many L. Okay, I can find a whole bunch of problems L that actually reduce to A. Okay, and hopefully including some L that we really think should not be in P. Well, if I can do that, and as I said, like we're thinking of like many problems L. We're not just thinking like 10, 20 problems. We're thinking like a big class of problems L. If we can do that, then you can say, well, that's pretty good evidence that A is not going to be in P. Right? Especially if you really think that some of these L should not be in P, really. Okay? Now here, the more L you have, the better, of course. The better the evidence. Okay, so this idea is going to basically motivates these notions of C hardness and C completeness, okay? So let me just define what these mean. So let curly C be some set of decision problems. Okay, we're going to say that the decision problem A is curly C hard, if basically every problem in this curly C reduces to A. Every problem in this class, in this set of problems, reduces to A. So A, in some sense, right, is harder than every problem in C. Okay? So technically speaking, you would say like A is at least as hard as every problem in C, but it's okay to think of it as A is basically harder than every problem in C, right? A is greater than every problem in C. And there's a very like related notion here, which is C completeness. And basically, it's very simple. A problem is C complete if it's C hard, and it's also in the class. So what you don't see there is A is C hard, and A is also in this class of functions, set of functions. And the interpretation here is that A is the hardest problem in C. Okay. So let's make some observations now. The first, so suppose that A is C hard. The first observation is that now look at, if there's a problem in C that is not polynomial time solvable, that's what this means, right? It's in C, it's in the class, but it's not in P, meaning it's not polynomial time solvable, then you know that A cannot be polynomial time solvable because, right, by definition, A is the hardest problem in this class. So if there's some problem in this class that's not polynomial time solvable, definitely A is not polynomial time solvable. The other observation is that now if this hardest problem in the class A is polynomial time solvable, then every problem in this class is polynomial time solvable, right? Just again by the fact that A is supposed to be the hardest problem in this class. Well, if C, yeah. Okay, so keep those in mind. And you know, when you say like A, every problem, when you say that A is in P, implies that every problem is in P. Why is that the case? Because every problem in C reduces to A. So if I have a polynomial time algorithm for A, then I get a polynomial time algorithm for any other problem in this class C. And you can, in some sense, think of this as saying, you know, A encodes, in some vague sense, all the problems in C. Okay, so that's interesting. Okay, so again, coming back to our goal, find evidence that, let's say, TSP is computationally hard. So what we're going to try to do is, we're going to say, okay, if A is C hard for a really big set, a really big class C, then, you know, you can say that's some evidence that A is computationally hard, right? And as we said, the bigger the C, the better. Okay. So we want to find this class, this big class of functions, C, such that, let's say, TSP is C hard. I mean, is that, I don't know if that's even possible at this point, but that will be our goal, nevertheless. Okay, so then the bigger the C, the better, fine. So let's go for full glory. Okay, so we want to know what's a good choice for C if we want to show TSP is C hard. And our first attempt is going to be basically C is the set of all languages. Okay, so can it be true that TSP is C hard? No, right? Why it cannot be true?
Well, because we know it's at least decidable because we brute force it, but there are undecidable languages.
Right, yes. So very good. So one thing now we should observe about all these problems, SAT, TSP, knapsack problem, theorem proving problem. These are all problems that are decidable, okay? Why are they decidable? Because there is an algorithm that solves it, and we call this algorithm brute force search. BFS, not breadth first search. Okay, so in this lecture, BFS is brute force search. So why? Because let's take the SAT, satisfiability problem. Given a propositional formula, you want to know if it's satisfiable or not. What's a brute force search algorithm that decides this problem? Well, you go through every possible assignment to the variables one by one, and you check for each assignment of the variables, does that satisfy this given Boolean formula or not? If you find one assignment that satisfies the formula, you output yes. But if you go through every possible assignments to the variables and you have not found a satisfying assignment, then you say no. For TSP problem, when you're trying to find a cycle that visits, a minimum cost cycle that visits every vertex, basically you go through every possible cycle one by one and check if it works. Okay? Theorem proving problem. Okay? Is there a proof of a given theorem of length at most 1,000,000? You go through every possible proof of length 1,000,000 one by one. You check if it's a valid proof or not, one by one. These are all exponential time algorithms, right? Because the space that you're searching is huge. There are exponentially many possible assignments, possible cycles, possible proofs. But the point is that they're all decidable, okay, exponential time. But if we take C now, coming back here to be the set of all languages, well, we know, for example, the halting problem is not decidable, right? So the halting problem would be in this complexity class C, and you're telling me TSP is reducible to the halting problem. No, the other way around. So you're saying to me that halting reduces to TSP, right? And that's basically not true, okay? So the fact that you can solve the TSP problem is definitely not going to imply that you can solve the halting problem. Okay, so this doesn't work. Fine. Then our second attempt will be the following. We're going to try to set C. Again, we're going for the largest C that we can go after. We're going to set C to be the set of languages decidable using brute force search, BFS. Okay? So now we're going to ask, can it be true that TSP or SAT or whatever is C hard for this class? Well, to answer this question, we have to really come up with a language that somehow captures problems that are decidable using BFS, brute force search. So, and this will be our, what we'll do next, basically. Okay. So we want to come up with a complexity class for BFS. How can we identify problem solve using brute force search? And we want some kind of reasonable definition for this. Okay, and I'm gonna try to come up with a reasonable definition now. Now let's look at these problems: knapsack, TSP, SAT, theorem proving problem, and ask ourselves what is common among these problems. Well, one thing that's common is it seems pretty hard to find a solution to these problems. So given a SAT instance, it seems hard to come up with a satisfying assignment. Given a TSP instance, it seems hard to come up with a minimum cost cycle, and so on. But there's an interesting thing about these problems. It's actually, if you look at it, quite easy to verify a given solution. So let's say the satisfiability problem. If I give you some instance, if I now give you the satisfying assignment that makes this instance yes, then you can easily check that indeed this satisfies the Boolean formula. If I give you a theorem and a proof for that theorem that uses at most whatever symbols, you can indeed check that this is a valid proof for the theorem. You just have to check, does does one thing follow from the previous thing, and so on. So the logical implications are correct. And so on. So for all of these problems, if I give you the solution, you can verify that it's indeed a correct solution. Okay, so this is basically what I said. So given a satisfying assignment to a SAT formula, you can easily verify that indeed it satisfies the formula. Given a cycle that visits every vertex in a graph, you can indeed verify very efficiently in polynomial time it visits every vertex. Given a proof, you can verify it's a valid proof, and so on. And in this context, we often call these solutions, so these blue things, they like represent the solutions, right? They're often called actually proof. Okay, in this context, solution is a synonym of proof. Okay, so we say that these solutions are a proof for the fact that this instance is in the corresponding language, it's decidable. Okay, so when you give a satisfying assignment for a given Boolean formula, that satisfying assignment is a proof that this formula is indeed satisfiable, and you can check that this is indeed a valid proof in polynomial time, let's say, efficiently. Okay, so what does brute force search do then with these problems? It basically goes through all possible solutions or proofs, one by one. There are exponentially many of them, but it goes through them one by one to find a solution. And the point is that it's like the space of all the proofs is like a haystack, and the proof is like a needle. Okay, you're trying to find this one proof, possibly like one proof that is in this big haystack. Well, the good thing is, like, if you see a needle, it's easy to distinguish it from hay. Okay, so the proof, you can indeed verify that it's a correct proof. You can identify the needle. But the problem is, this haystack is quite large. It's exponentially large, and this algorithm takes a lot of time to find it. Okay, so now this basically now motivates the complexity class NP. Okay, so informally, the class NP, the complexity class NP, is the set of decision problems such that whenever you have a yes instance, whenever you have an instance in the language, there's a simple proof for this fact. So what does simple here mean? Simple means that, first of all, this proof, the length of this proof is going to be polynomial in the input size. Okay, because it's exponential size, then I cannot verify that proof efficiently. And the second thing is, well, basically what I just said, the proof should be verified, checked in polynomial, can be verified or checked in polynomial time. Okay? So that's informally. Let's do it now formally. So formally, this is the way we would define it. So we say that a language A is an NP if there is a polynomial time Turing machine or a polynomial time algorithm. We'll call it V. Okay, so we usually call Turing machines M, but in this case we're going to call it V because this is going to be a verifier algorithm. There is some polynomial P such that for all words X, for all possible inputs X, X is going to be in the language if and only if there is some U. U is the proof. There exists some proof, there is some solution U of polynomial length, at most polynomial length, that leads the verifier to yes, 1. Okay, so the verifier only outputs 0 or 1. Okay, it's a decider. Okay, so what this means informally, right, again, x is in the language if and only if there is a polynomial length proof u that is verifiable by a polynomial time algorithm. Okay, again, think about the examples. For SAT, the proof is a satisfying assignment. Okay, and the verifier basically takes a satisfying assignment, plugs it into the formula, and checks, indeed, yes, it satisfies the formula. Now, let's be clear about this by implication, if and only if. Okay, so what that means is that if x is in the language, there's some proof, u, that will lead v to accept. There's some, let's say, satisfying assignment that leads v to accept. But on the other hand, if x is not in the language, then no matter what proof you give me, because there is no proof, right? If x is not in A, there is no proof. But that means that no matter what you give me as proof, my verifier should reject, should output 0. Okay? So if you think about the satisfiability problem once again, if you give me an unsatisfying Boolean formula, well, doesn't matter what proof you're trying to give me. Okay, you might give me any assignment to the variables you want. When I plug it in, I will see that it doesn't satisfy the formula because it's unsatisfiable. Right? So you cannot trick me into thinking that an unsatisfying Boolean formula is actually a satisfiable one. I will be able to tell difference. Okay, so this is basically the complexity class, NP. SAT is an NP, right? X, the input x is a Boolean formula. The proof u is an assignment to the variables that makes x true. TSP is an NP. The input x is a graph with edge weights and a target t. The proof is a cycle of cost at most t that visits each vertex exactly once. Right? Once you give me this proof u, my verifier is going to check, okay, this u you gave me, is it indeed a cycle? Yeah, okay, that's easy to check. I'll add up the cost of the edges. Is it indeed at most t? Yeah, okay, good. That's easy to check. And then I'll also check, does it visit each vertex exactly once? Yeah, okay, that's easy to check as well. So, cool. Okay, and so as I said, proof is like a synonym for solution. Another word that's often being used that you'll hear is a certificate. Okay, so these are basically all synonyms. So this proof u certifies the fact that x is in the language. You know, so u is called a proof, a certificate, a solution, whatever you want to think of it. You can use any of these things. So, okay, so let's make now two observations about this class NP. First of all, every decision problem in NP can be solved using brute force search algorithm. Okay, that better be the case, otherwise it doesn't really capture brute force search. So, why is that the case? We've already discussed this. Like you can just go through all possible proofs u and run v x comma u. If one of these proofs leads v to accept, you accept. If you go through every possible proof but none of them led v to accept, then you reject. The second observation is that this is a pretty big class. Okay. Most of the problems that you're going to come across in your life, very high probability that it's going to be in NP. Most problems are going to be in NP. But just to give you some other convincing fact why this is a big class is because, well, at the very least, it contains everything in P. Okay, contains everything in P. So the picture looks something like that. So why is that true, though? Why does it contain everything in P? Well, okay, I mean, it's pretty straightforward, actually. So let's say that we have a problem, a language A that is polynomial time solvable. So it has a polynomial time decider. Let's call it M. Now, we want to show that A is in NP, which means that we have to come up with this verifier Turing machine V, right? So this V, this verifier Turing machine, is going to take as input, well, the real input X, obviously. But as the proof, it will just take the empty string, meaning I don't care about the proof. Now, why don't I care about the proof? Because, well, V is just going to run this polynomial time decider M and return its output. It's saying, like, I don't need your proof. I can decide it by myself, right? Yeah, it's true. Yeah, so that's the picture. So NP is contained in P. And most people think, actually, that NP contains much more than P. Okay? And actually now, you know, if we refine the picture a little bit, if we look at these problems that are NP complete now, right? If you remember, NP complete problems represent the hardest problems in NP. So they are going to be basically somewhere in this picture, but they're definitely basically not going to be in P. If you believe that P is different from NP, right? So if you believe that P is different from NP, you believe that in NP there's a problem that's not inside this P. But if there's a problem that's not inside this class P, well, definitely the problems, NP complete problems, which are the hardest problems in NP, they're also not going to be in P. Okay, so again, we want to find evidence that these problems are not in P. So the question is, of course, could it be true that one of them is NP complete? And actually, before you even ask that, is there any decision problem that is NP complete? Is the question you should be asking. Because the fact is that, okay, we made this definition, and when you hear that definition, you should be skeptical in the sense that, is this even a useful definition? Because it's a very strong requirement for a function, for a language to be NP complete. Every problem in NP has to reduce to that problem. Wow, like that's a very strong requirement. Why would any problem satisfy that requirement? I mean, first time I heard this, I didn't think that there would be such a function. Okay? So is there any decision problem that's NP complete? And another thing to keep in mind is, as we said, if A is NP complete, it's like A encodes all problems whose solutions can be efficiently verifiable, right? We know if we could solve in A in polynomial time, we could solve every problem in NP in polynomial time. Okay, every problem in NP reduces to this problem A. Like really, really seems like a very too strong of a requirement. So you would be totally reasonable if you guess that, you know, this definition sucks. It's like, it's useless because no problem can be NP complete. But turns out that these two guys, Cook and Levin, are, I guess, heroes for this lecture. They showed basically in early 70s that satisfiability problem, SAT, is NP complete. That is, every problem in NP polynomial time reduces to SAT. Okay? Now, they proved this independently. Cook proved it in 71, Levin in 73. At the time, there was limited communication between Russia and the United States, so they weren't really aware of the results of each other, but they basically proved this independently in the early 70s, which is quite an astonishing fact. And then right after, basically in 1972, Richard Karp published a paper, Reducibility Among Combinatorial Problems, and he presented basically 21 other problems that are NP-complete. Here are some of them. 0-1 integer programming, the clique problem, set packing, vertex cover, set covering, blah, 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 blah. There's max cut in there, job sequencing. Very fundamental and natural problems. Most of these problems are graph problems, but as you hope already know, like graph problems basically encode very natural problems, right? So these are very fundamental problems, all of them. And today, you can ask, well, that's in the 70s, 1972. What about today? Well, we know now like thousands, even actually tens of thousands of problems that are NP-complete, including all these problems, SAT, TSP, knapsack theorem proving. And a good resource for NP-complete problems is this book from 1979, actually, by Gary and Johnson, Computers and Intractability. It contains a lot of hundreds of useful NP-complete problems. And you know, there are not many books, there are not many computer science books written in the 70s that is still relevant today. But you know, the field is progressing very quickly, but this book is definitely still relevant. Here are some other examples, just randomly picked examples that are NP-complete. Longest common subsequence problem. Given a set of sequences and a number k, is there a subsequence of length at least k that's common to all the given sequences? So we sort of saw this problem earlier, but this is now a bit different because you're not just restricted to two sequences. You can be given an arbitrary number of sequences. Subset sum problem. I think I mentioned this earlier in the course. If you remember, given a set of integers and a separate integer k, is there a subset of these integers that sum to k? NP-complete. I'm giving you these examples so that you can appreciate the wide range, the wide variety of NP-complete problems. They don't all look like each other, okay? So they look totally different, but they're all NP-complete. Longest path problem. Given a graph and an integer k, is there a path of length at least k? Now, this should be somewhat surprising because if you ask the shortest path, that's polynomial time solvable. If you ask for the longest path, that's NP-complete. Sudoku, when you have arbitrary dimensions, is NP-complete. Super Mario Brothers. It's true, someone actually showed that given a Super Mario Brothers level, if you ask the question, is it completable? That's an NP-complete problem. Yeah, some people have too much free time, I guess. Tetris is NP-complete. Given a sequence of Tetris pieces and a number k, can you clear more than k lines? And I think this was proven in 2002 by Professor O'Donnell's roommate. Yes?
Can you compare the hardness of two NP-complete problems?
Right, so that's a good question. I'm going to come back to this, but yeah, so if you talk about two NP-complete problems, they reduce to each other. If A and B are NP-complete problems, A reduces to B, B reduces to A, by definition. I have a slide for that, yeah. Actually, maybe it's this one. Okay, so, and many more, right? So there are, like, as I said, tens of thousands of problems that are NP-complete. They come up everywhere, in every field of science and engineering. they're there. And right, so and amazingly, coming to your point, they're all in some sense equivalent to each other. Why? Because if A and B are NP complete, then basically by definition, A reduces to B and B reduces to A. Okay, because if B is NP complete, that means that every problem in NP reduces to B, but A is in NP, so A is one of those problems that reduces to B. But similarly, if A is NP complete, every problem in NP reduces to A, but B is one of those problems, so B reduces to A as well. So that means, in some sense, that you can go from one problem to another problem in polynomial time. They're like, in that sense, equivalent. Okay, so now let's ask the question, the natural question, how do you prove that some problem is NP complete? So you want to show that A is NP complete. That means that first A has to be in the class NP. That's usually the easy part. And that for every problem B in NP, you want to show that B reduces to A. How can you do that? Well, the good thing is, if there is one problem that you know is NP complete, so suppose that you know there's some language problem L that is, let's say, NP hard. Doesn't have to be even an NP. So we know in that case that every problem B in NP reduces to L. Then you want to show A is NP, your problem A is NP complete or NP hard. Well, you can just show that L, this one problem, NP hard problem L, reduces to A. Reductions are transitive. So if every problem B in NP reduces to L, and L reduces to A, then every problem B reduces in NP reduces to A. It's a transitive relation. So that shows that A is NP hard too. So that's pretty nice. So that means you can follow 3 steps if you want to show, and we're gonna do this in the next lecture. You want to show some problems NP complete, show that first A is an NP, usually the easy step. Then second step, pick your favorite NP complete problem, L. Super Mario Brothers, Tetris, whatever you want. And then show that this problem reduces to your problem in polynomial time, which means that given a polynomial time algorithm for A, come up with a polynomial time algorithm for this language L, for this problem L. So that's cool. That's nice. But you should be asking now the following question. You know, how did Cook-Levin show SAT is NP complete? I mean, they didn't have any NP complete problem in hand, NP hard problem in hand to work with, right? So they actually indeed had to do the hard work. They actually had to show that every problem in NP reduces to SAT. And I will show a sketch of this basically in the next lecture, so we're not going to do it today. So this is also an advertisement for the next lecture. Okay, so when a problem is NP complete, when a problem is NP hard, that seems like pretty good evidence that this problem is not NP, because you would be reasonable, quite reasonable, to think that NP contains some problems that are not polynomial time solvable. Okay? But of course, this is all good. This is good evidence if you believe P is different from NP. And you would be a totally reasonable person if you said, you know, P is different from NP. But is P different from NP? So that leads us to the famous P versus NP question. Okay. Now, before we discuss the P versus NP question, let's address the elephant in the room, which is, What does NP stand for anyway? Right? I didn't even tell you that. So is it not polynomial? Is it non-polynomial? Is it no polynomial? Or is it nurse practitioner? So it's actually none of the above. So please, this is very important. Like, don't think that NP stands for not polynomial or something like that, because it doesn't. So what it stands for is non-deterministic polynomial time. Non-deterministic polynomial time. And the reason why it's called non-deterministic polynomial time is because it turns out that languages in NP, in non-deterministic polynomial time, are languages that are solvable in polynomial time using a thing called non-deterministic Turing machine. So we did not cover non-deterministic Turing machines, and we're not going to cover it. But you can think of it as follows. So when we talked about DFAs, deterministic finite automata, in the homework you had SFAs, finite automata with super magical superpowers. These are actually called NFAs in the literature. N stands for non-deterministic. So these SFAs that you dealt with are actually non-deterministic finite automata. And the relationship between basically a DFA and an NFA is the same kind of relationship between a deterministic Turing machine and a non-deterministic Turing machine. So a non-deterministic Turing machine is a Turing machine with magical superpowers that can check multiple computational paths at the same time. And if one of them leads to accept, it accepts and so on. But we're not going to discuss that. It's not important. But that's where the name comes from. Okay? And in the early times when people were trying to figure out the name for this complexity class, there were some other contenders. Herculean was one that was considered. Formidable. Hard-boiled. And I think the most interesting one is PET. And PET is nice because it's sort of adaptive. So if you don't know, we don't know whether P is equal to NP, so you can say, okay, this is the class possibly exponential time. But let's say somehow one day one person shows that P is different from NP, then we can change the name to provably exponential time. But you say, okay, what if someone shows P is equal to NP? Well, then you can say previously exponential time. So it's a pretty nice name. But yeah, we have NP. Yeah, the physicists have like all cool names for their stuff, like quarks and black holes and dark matter, dark energy. We're stuck with P and NP, unfortunately. Okay, so the P versus NP question, whether P is equal to NP, as we discussed in this course, it's a $1 million question, but really this understates the importance of the question, okay? Because it's really like psychologically much more important than that. We're pretty convinced at this point, after like years of research in this area, that this is like one of the deepest questions that we've ever asked. If P is equal to NP, that would be amazing. It would have possibly amazing implications in every field of science and engineering, that you can solve these problems efficiently. If P is different from NP, and you're able to prove that, well, we think that this is going to lead, the resolution of this problem is going to lead to really amazingly deep insights about math and computation. So it's bound to have applications in other areas as well. And we are really, let me emphasize this one more time, very far from answering this question. We can basically define much simpler questions for ourselves. We can define baby versions of the P versus NP question, and we don't have an idea how to solve even the baby versions of the question. So we're pretty confident that when this gets settled, I don't know when, maybe in 100 years, 200 years, it will be very insightful. Okay, so these are the two possible words. Either P is equal to NP or P is different from NP. This is the world in which P is different from NP. When P is different from NP, you have this class NP complete problems that are definitely not going to be in P. And you have all these problems that are NP hard. Not all NP hard problems are in NP, right? If an NP hard problem is in NP, that's NP complete. So you have that NP hard problems. And on the other hand, if P is equal to NP, then P equals NP complete. And you might have other problems that are NP hard that is not part of this class. Now, to show that P is different from NP, what you can do is you can pick your favorite NP complete problem and show that it cannot be solved in polynomial time. Right? Or if you want to show that P is equal to NP, pick your favorite NP complete problem and show that it can be done in polynomial time. It can be solved in polynomial time. So really, this famous P versus NP question, one of the deepest questions that we've ever asked, is equivalent to asking whether Sudoku is in P or not. This problem is equivalent to whether, because Sudoku is NP complete, so maybe that's the favorite NP complete problem you pick. This is an equivalent statement. So what do experts think about this question? So there are two polls done in 2002 and then in 2012, 10 years later. In 2002, 100 experts participated. In 2012, 152. And here were the results. So in 2002, people who thought P was different from NP was 61%. In 2012, that came up to 83%. People who think P equals NP stays roughly the same, about 10%. Some people, it's independent of ZFC. So ZFC, these set theory axioms. Some people think that you will not be able to prove P equals NP or the other way around, P is not equal to NP using these axioms. That's what that means. I think you'll understand what that means more next week on Thursday. DC is don't care. Some people don't care. And DK is don't know. That's quite remarkable that in 2012, only one person says don't know, but like in 2002, it was 22 people, 22%. So here are some common arguments that you'll hear on why P is different from NP. So the first common argument is that, well, if P was equal to NP, someone would have found an efficient algorithm for some NP complete problem. So these NP complete problems, as I said, they're everywhere. And people have been trying to solve these, probably not on purpose, but without knowing that these are NP complete, trying to solve these problems really hard. And no one has been able to do it. And actually, no one has been able to come up with a sub-exponential time algorithm even. Okay? So it's possible that a problem is not polynomial time, but also not exponential time. It's somewhere in between. So it could be like what's called quasi-polynomial time, for example. So no one has been able to come up with something better than exponential time. Whether this is convincing or not, I will leave it up to you. Okay, whether this argument convinces you. The second argument you'll hear is like, well, verifying a given solution is quite easy. From our experience, we know that, if you give me the solution if I give you the solution to a homework problem, it's sort of easy for you to verify that, oh yes, this is indeed a solution. But if I ask you to come up with a solution to a homework problem, it's not always easy, right? And in some sense, seems to require some sort of creativity. In quotes, I don't know what that exactly means, but some people use that term. And you can ask, if P is equal to NP, it seems like creativity can be automated. And people think that that's not the kind of world we live in. Okay. Again, it's up to you to decide whether you're convinced by this or not. For me personally, the most sort of convincing argument or an argument that flips the scales towards P different from NP is the following one. So recall this complexity class inclusion. So we saw that this log space is contained in P, is contained in P space, is contained in exp. And now if you ask, where does NP lie in this chain? Here it is. We're not proving this, but it turns out L is contained in P. We saw P is contained in P, and it can be shown, it's not hard to show that NP is contained in P space. But now, okay, here's the thing. We know that L is different from P space by the space hierarchy theorem. So L is different from P space. That means that either L has to be different from P, or P has to be different from NP, or NP has to be different from P space. They cannot be all equal. Okay? So then you can say, well, why not? Maybe the one that's not equal is maybe P and NP. But also look at the following. We also know that P is different from exp by the time hierarchy theorem. And that means that either P is not equal to NP, or N is not equal to P space, or P space is not equal to exp. One of those three has to be true. And then again, you can say, one of them has to be true. Well, it could vary. Like most people think that all of them are not equal, by the way. And you might say, well, why not P and NP? Okay, so that's an interesting argument. So how do you deal with NP-complete problems? There are several things you can do. Like you don't want to throw the towel and give up. You can try to focus on tractable subproblems. Let's say you're given a graph problem that asks you to do something with answer a question about the graph. Maybe you cannot answer it for general graphs, but when the graph is a bipartite graph or when the graph is a tree, maybe you can solve it. Okay, so maybe you want to focus on those kinds of special cases. You can look at heuristic algorithms. These are algorithms that are not guaranteed to be correct on every instance. And in practice, heuristic algorithms are used a lot. You can try to do better than brute force search. Maybe try to get something better than n factorial or 2 to the n. And you can try approximation algorithms. Not get the exact solution, but an approximate solution to your answer. And this will be discussed basically next week. All right, so that's basically, I have a summary, 2 slides of summary. You can check it on your own. And then next time will be how did Cook and Levin show that SAT is NP complete? That's a pretty interesting question. And examples of reductions that show other problems are NP complete. Hey.